All good?
Yep.
Great. Thanks so much. It's really a pleasure to be here. I really appreciate the invitation and the opportunity to speak to you today about this book. This is the new book project, which is called Shaping Science. You can now see without the background getting in the way. And it just came out with the University of Chicago Press. And so I'm going to give you sort of the overview of the book length argument here, which means there's lots of opportunities for questions and discussions. There's lots more that I'm not going to talk about today that is in the book, and I'm happy to discuss. It has to do with my work, an ongoing work with robotic spacecraft teams. I know what's interesting about this series is that you've heard not only from astrobiologists and planetary scientists, but also from those of us who study your community and from people who do outreach and from people who are involved in the more humanist and social science side, which is very exciting as I hope this is informative for your work. In particular, the kind of work that I do as a sociologist of science and technology is to understand how scientists work together effectively in teams and what implications their teaming decisions have for the way they do science, the questions they ask, and the kinds of scientists that they ultimately produce. So I was attracted to this question of studying this particular group of scientists and these mission teams sociologically, largely because from the sociology of science, we know that scientists have their own practices and teams and local cultures. But also when I started to dig into the organizational sociology literature, I realized that these cultures actually play a really significant structuring role, especially when we look at flatter hierarchies. So the move in the last 20 or 30 years in the sciences and in engineering and in the tech sector towards much flatter organizations, much less bureaucratic organizations, means that we're relying more and more heavily on cultures behind the scenes to do a lot of the work that structure used to do sociologically. We also know from old-fashioned and older studies in not necessarily old-fashioned, but older studies in the sociology of organizations, that the way that different organizations are structured has significant impacts on their outcomes. So studies of factories, for instance, under the transition from communism to capitalism in Eastern Europe or in China, show that even with the same people and the same kind of instruments or the same kinds of tools that they're using, if they organize themselves differently, you end up with different kinds of values for their for what they produce. You end up with a slightly different sort of sense of what the production is, et cetera. So this structure and more recently this culture really impact the kinds of products that emerge when people work together in some kind of organizational unit. And if you are familiar with computer science, this is known as Conway's law, which is the idea that there will be a strong degree of isomorphism between your organization's communication structure and the structure of your code, right? So this is the kind of thing I'm looking at in the sciences in particular. I'm also inspired by some work done by a sociologist of science who studied NASA before. This is Diane Vaughn, who's at Columbia University. She has an amazing book on the Challenger launch, what looks at the critical decision to launch that was based in a particular form of organizational culture. And she asked this provocative question at the close of the 20th century, which is, how do the organizations for which you work affect your own knowledge practices? So these are the kinds of questions that I come into the field with as an organizational sociologist studying scientists as they work together. And now what's interesting, of course, is that you as scientists have a very powerful way of talking about these kinds of pressures as well in your work. Locally, this is known as the kind of personality or style of a mission. And this is what one of my more senior interviewees expressed very early on in my fieldwork. Every mission is like a living organism. It has a personality and it has a style. And that personality and style is gained at the beginning of the mission and it never changes. The people who migrate through the mission change. You can change out the people, but you still have that same mission personality. So what this person is speaking to is the sense that there is something about the organizational unit that is a mission team, that outlasts or outlives the individuals who move through it. And for those of you that have had an experience working within a lab or working within a collaboration or working on a mission that lasts for decades in some cases, you understand that when you come into those places, you have to be attuned to the local organizational culture, the local way of getting things done, and that starts to dominate the ways in which people interact on that mission team. So this is precisely the thing that I'm going to unpack for you today, and the kind of role that personality and style plays in the production of science and planetary science and astrobiology. To do this, I'm going to rely on ethnography. I've been embedded with the planetary science community since about late 2005, so over 15 years now, working with a variety of different missions in sequence, some very early in their production, some in the operations phase, some just ducking in and out to see how things are working in their meetings. But largely this involves what we call the systematic recording of human cultures. And that is that as an ethnographer, it's not like being a journalist where you just visit a little bit, you conduct some interviews. You spend a really long time with a particular community of people. Back in the olden days when ethnography was first getting started, anthropologists would go to some island in the middle of nowhere and be like, what are the natives doing? And write about it. We don't really talk about it like that so much anymore with those kinds of colonial overtones, but certainly this is the kind of expectation for somebody even working with a science team, that you should be there for a long period of time, understand how things are done around here, what the standard narratives are, how people explain their work, and how they describe their relationships with each other. And this involves also interviewing, gathering narratives and experiences from across the mission, observing largely mission meetings, especially operations meetings, and to try to do that from as many sides of the organization as possible. So it was just as important for me to talk to the grad students and the undergraduate research assistants over the summer who were doing work in the lab as it was to talk to the scientists who were PIs or who were team affiliates, as well as people who were higher ups at NASA, in order to understand how these teams worked. It also meant going to conferences, going to planning meetings, going to team weddings even, and even the robot funerals, which I'm happy to talk about also in question. And often when I explain those work to planetary scientists, I explain that it's kind of like if any of you have ducked into the physics side, that what I'm trying to do is understand what the underlying field lines are, the currents are, that are directing and guiding the ways in which people interact. So, if you think about a planetary system that's very complex, like Saturn or Jupiter, right, where you are trying to detect as many particles as you can in that environment, figure out what's their charge, what's their spin, what's their polarity, what are their characteristics. And then by virtue of how they're moving in the system, you can kind of build up an underlying model of what that ebb and flow and flux of the underlying magnetic field is. And that's the kind of thing that I'm doing as an organizational ethnographer, is trying to figure out, based on how all these scientists are working together, where they're moving, who picks up what spin and who exits the system, et cetera. What are the kind of underlying invisible field lines that are guiding people through? So the main point of the book is to argue for a concept that I call organized science, and this has three parts, two of which I'm going to talk about today. The first is that we need to think about science teams as organizations. They are organizational units, they have structures, they have cultures, they have rituals. You can ask Dr. Schmidt someday about the rituals on the Europa Clipper mission that involve things like large monoliths. And they have particular ways of interacting that characterize what it's like to work on that team. And this basically describes what it's like to be a member of that team. And so I argue that we should be using the tools of organizational sociology to understand these units as science teams and as missions. And then secondly, I think we need to do that because of the shaping role that these organizations have on the products of scientific work. So that is, how you organize your team shapes the knowledge you produce. And this includes your knowledge of objects in the world, the instrumentation you use, the data sets you produce, and even your colleagues. I'll leave the last point for later for those of you that are interested in reading the book. So to make this point, I am going to describe two missions that I studied in detail. These missions occurred at largely the same time, and their operational phases began and ended within months of each other. They involved largely the same or very similar roster of institutions, both of them led through a single institution that's a NASA-affiliated center. And they had many of the same people actually worked on both teams at the same time, but they had two very different organizational structures. And this was largely because of the changes that NASA made in the 1990s under Faster, Better, Cheaper, introducing a new category of missions that were competed with single principal investigators. And so the key difference here is that one of these missions is the classic flagship, where you have many different, PI-led instruments on at the same time, and everyone has their own kind of expertise and their own zone of authority, as opposed to these much more single principal investigator, much flatter kinds of organizational units that we see with the single PI teams. So the goal here is not to value one of these missions over the other. These are both extremely successful, high-profile missions, strong public appeal, hundreds and hundreds of publications. There's no reasonable way in which a social scientist could come in and say that one is better just generally than another. So that is not my purpose here at all today. My purpose is to examine how they worked and generate any kind of extensible findings from the patterns that I saw on each of these missions around how they each worked. And what that means is that each mission is going to be really good at some things and not as good at others, because all organizations are like that. But largely, subjecting them to this form of organizational analysis lets us see what happens when you insert a form of organizational variation on two different teams. This is as close to a natural experiment as I can possibly get. And this is why I will refer to these missions as Helen and Paris throughout the rest of this talk. So you may be familiar with them by their other names, but I'm using these pseudonyms to remind you that these missions have now been through this analytical process where the purpose is now to think about them more generally as examples, as case studies of a particular organizational form in operation in a scientific context. And that means that they'll have a lot in common with other kinds of organizations that share those characteristics, whether those are engineering and technical organizations, or whether those are religious groups or activist organizations or banks. There are certain things that they will now have in common by virtue of this organizational framing. So let me jump in and tell you a little bit about how science is done on each of these missions, or at least how resources are allocated on these missions, which is the principal way in which we end up determining the scientific results and the data that returns from these teams. Let me begin with Helen. So Helen is a multi-year flagship touring mission to the Saturn system. It had 12 different instruments mounted on it. And because there was a scan platform that was initially descoped early on to save money, the instruments were tacked onto the spacecraft pointing in different directions. And this means turning the spacecraft between instrument observations is key to figuring out who can observe and when and how to allocate resources. Now, this mission chose, they were a much sort of more bureaucratic structure in the sense that each team had its own PI or leader and then its own group of scientists, and those groups didn't necessarily mix with each other, except that this team chose a matrix organization, which produces a light kind of mingling across those different units by bringing together scientists from each of those instrument teams that were interested in one or another property of the Saturn system. And those groups, those matrixed groups, the 5 cross-cutting groups, were responsible also for planning what the spacecraft would do when it moved past that part of the system. So there was a group of scientists, for instance, who were interested in the rings. And that would take scientists from each of those 12 instrument teams and put them in a rings group. And then that rings group not only shared what they were learning from their different instrumental perspectives, but also decided what the spacecraft would do every time it came close enough to observe the ring system. So the key problem for resource allocation on Helen was one that they called integration, and that I'll kind of gloss as a form of polyvocality. So that is, you have to respect as many unique voices as possible in order to assemble a feasible plan. Plans are not only feasible because it's something the spacecraft can execute. Plans are also considered acceptable once as many different voices as possible have weighed in to how that plan should be laid out. So I'll give you an example here on the left. This is a moment early on in my fieldwork where the team was trying to decide between 7 possible options for the tour for the spacecraft over the next 7 years. So they were trying to determine where the spacecraft was going to go and what it would be able to see over the next 7 years. You'll see that the different rows correspond to different scientific priorities, and the columns are the different tours. And what this group had to do was color in the intersection between the tour and the priority with how well that tour would achieve that priority, indicated in red, yellow, and green. And you'll notice there's not a lot of red, yellow, and green on the spreadsheet, right? There is some green, and then there's a little light green, and then there's a color they call it lemon lime, and then there's kind of a light yellow, and then there's an orange and even a pink, right? And the key thing here is to note that those 3 colors, red, yellow, and green, did not capture the range of opinions and needs in the room. And that was the thing that needed to be captured in the spreadsheet to move forward, was actually just how complex this was and how many different perspectives and voices there were. Now you'll note that there are numbers also placed in this spreadsheet, and that's because after they did this exercise, they realized that they had to provide a single, like, unified, like, average, weight for each of these tours, and that Excel didn't know how to compute an average of colors. And so they were like, well, let's put some numbers in and we'll figure out, relative weights and strengths. And then everyone was like, well, this is kind of ad hoc and this doesn't really work. And there was a lot of laughter about this. This is actually a team that had a tremendous sense of humor. But it demonstrates the complications of the problem of polyvocality, which is making sure that as many different groups can weigh in as possible. And the autonomy of those different groups to determine what the scientific priorities are is important to move forward. It's worth noting that the matrix organization meant that groups were making these decisions constantly amid the matrix at the lowest possible level of authority. These were not decisions that were made by PIs that were calling any shots. This was made by the scientists who were collaborating together. But in cases where there was a real butting of heads, as I described in the book, you could go to the project manager, the engineering hierarchy, to solve the problem. So there's actually a lot of conflict, clearly, when you have this many different scientists and this many priorities. And so the team had a very powerful form of talk associated with battle and political metaphors that encapsulated the difficulties associated with that conflict. So someone described, well, this is like Congress. You want to align yourself with this guy to get this observation, but sometimes you have to align yourself with those people. So there's kind of a politicking that had to go on if you wanted to get your observations through the process. People also talked about straw man plans that they battered down, and there were meetings where there was blood on the floor at the end of the day. I never actually observed blood on the floor at any of these meetings, but the use of this form of talk laid out the sort of the complications of entering into this space where you had to negotiate and make sure that as many of these different perspectives could move forward as possible. Another feature that I observed is that people did what I called a form of instrumental metonymy, and that is that they associated individuals in the room who were advocating for an instrument with the instrument itself. So I was in a meeting where someone said, oh, John, you need a few minutes to warm up here. And John didn't need any time to warm up. He was perfectly fine. The room was fine. It was the instrument that he represented that needed more time on the timeline to warm up before it took its observation. So, but interestingly, John here was metonymous for that instrument in the timeline. And I saw this occur across the mission as individuals were associated with particular parts of the spacecraft or particular roles in the spacecraft team. Another key appeal in putting together this polyvocal integrative plan was an emphasis on fairness. And so the notion here is that it was basically impossible to adjudicate between all of these different priorities because they were so incommensurate. How do you decide that this physics observation is or is not as important as a stellar occultation or as a geomorphological observation? Like, you can't, those are such different forms of science. So instead, the groups developed an emphasis on what they called fairness, and that is making sure that everybody had an equal or fair sets of trades that occurred, such that you could point to the fairness of the transaction to say that it had been appropriately done. And this resulted in some phrases that were said frequently on the mission, like, we can't make everyone happy, but we can make everyone equally unhappy. And the point here is actually equally, right? It's the fact that, that this had been equally and fairly allocated. You'll note, actually, I'll just draw your attention to the images on the left here. These are some of the visual supports that help people do this process of integration. So each of these stripes, the gray and white bars, indicate an hour of spacecraft time. And the colored bars that cut across are moments when an instrument would like to observe. And these are moments that scientists themselves went into the database and said, this is where I want to observe, and this is what I want to do. Now, you'll notice that in this section, of course, because this is a periap, so they're getting close to the planet, that there's a whole lot of instruments that want to observe at the same time, number one. And number two, that some of those instruments, the teams haven't decided amongst themselves who should be observing. So there's like 5 or 6 different requests from the same instrument happening at that time. So the goal of that meeting is to go in and figure out basically really like 1 or 2 of those instruments is going to be able to make that observation at a time. And that's where this conflict basically comes from. And then throughout, again, is a way of balancing the fact that this was actually very difficult work, and it put relationships on the line frequently. But those relationships were essential to actually getting the work done, as is often the case in flatter organizational forms. So the team had a form of humor that I call affective ambiguity, and this was a kind of combination of like positive affect and then this kind of ambiguous or sort of conflict-laden talk. So here's an example. I have some very good friends on the mission who would kick me in the teeth if I wanted to do an observation that conflicted with theirs, right? So I have very good friends, but they kick me in the teeth, right? And it's this combination, again, equally unhappy, right? That we're going to be equal but unhappy. So this combination of things happened frequently on the mission. It was a local way of not only sense making, but also talking about and processing the complexity of the work that they had to do. So that's what it looked like to work on the Helen mission. And I'll note that this was an extremely complex mission, and studying Helen is like studying the United States, right? Like you can't just spend time in Kansas and decide that that's how the entire US is. So the difficulty with Helen was making sure that I visited as many units as possible that all had their own way of working, that all had their own way of doing fairness, that all had their own little local cultures, and trying to understand then generally what could be ascribed to the mission as a whole. But let me now skip to the other side of the asteroid field and tell you what it's like on Paris, which was a multi-year roving mission to Mars. It sent 2 identical robots to different parts of the red planet. And this was a smaller mission team that was led by a single principal investigator. And it's what I would identify in the literatures in organizational sociology as a charismatic collective. So that is, first of all the scientists belong to the same team, and they were emphatically collectivized. That is, the notion was this was a collective team, that there's no hierarchy between members of the team, that there are people had particular roles that they played, like some people were in charge of making sure an instrument was healthy, and others were in charge of making sure some observations got to that instrument or requests got to that instrument. But in principle, the most senior scientist who had cut their teeth on Viking was at the same level organizationally when it came to discussions as the graduate students who were just joining for the first time. So the notion was that everybody joined this collective unit. And I say charismatic because it was led by a single principal investigator in line with a form that Max Weber calls a charismatic organizational form. This doesn't just mean that the person themselves was charismatic, but it means the way the organization was set up was such that individuals felt a tremendous commitment to the cause, and that cause was often embodied by this individual who was the PI. Now, unlike the problem on Helen of polyvocality, the problem on Paris was one of unilateralism, unilateral agreement, and they signaled this through what they called consensus. So that is, consensus means that we all agree to this plan, and good plans, therefore, are the ones to which all of us agree. So the key element here was to get to the end of their planning meetings, which when I observed them took under an hour for each robot, to get to the end of that planning meeting and have a single idea of everyone's shared single idea of what the robot should do. So you can't just kind of like just do this out of nowhere. There were tons of cultural and structural elements in the meetings that helped produce this as a moment. So I'll show you here an image on the left, which is from the live feed cameras that were supporting the operations meetings, planning meetings. The image on the top left is one that we saw quite frequently. It took a picture from the robot's point of view, looking out over the terrain, and then it's all marked up with arrows and stuff, right? And the purpose here is to make sure that everybody is starting off on the same foot, actually literally in where the rover is. They're all from the same rover perspective, looking at the same things as the same things. There's no argument about whether or not this particular area represents high silica, like it says in the map, right? So we all see the same things as the same things. And then also the image at the bottom is at the control room at the central headquarters at the NASA center that was commanding. It looks like no one showed up for work that day, but actually each of these placards represents someone who's phoned in on a teleconference line. So it reminds you that these are all the people you need to agree with. And additionally, the tables are set up in a circle, and the circle was supposed to remind you that we are all in this collective, and we're all on the same team, and we're all in the same position. So you could always appeal to the PI if necessary, but the PI really made decision-making move down into that collective unit, and he spent more time doing bottom-up work, helping people come to that form of consensus than he did necessarily coming in and saying, this is the plan. I talk about that more in the book, and I can answer questions about that later. So the emphasis moving forward was on happiness and unilateral assent. And what this meant is that at the end of the meeting, in order to decide this is what they'd all agreed to, that the chair of the meeting, which is a rotating role, would go around the room and ask everybody on the line if they were happy with the plan. And everyone had to say, I'm happy, before they proceed. And I often joke that you should try this at your next lab meeting, right? And I mean that as a joke because you can't just walk in and ask everyone if they're happy, because they're not always. And also because you have to do a ton of work beforehand, in that hour beforehand, before you can get to the point where people will say, yes, I'm happy, because they felt like they've been part of that process the whole way through. And so when I spoke to one of the people who worked as a chair of these meetings, again, this rotating role, he said, well, the whole purpose here is to make sure that everyone feels a sense of ownership over the plan. The whole point of the meeting is not just to come up with a plan, but to have a process that brings a sense of ownership for everybody who's involved. And we see this also, this kind of ownership language in the Valley as well. The spacecraft itself was identified as a unified entity, so a Swiss Army knife with lots of different capabilities, and you could use any of them you wanted to. I was at the meeting on the day when the guy who built one of the particle spectrometers asked for his first visual image from the camera, and everyone like stopped, and there was cheering on the line for like 2 minutes where they were all like congratulating him because he'd finally gotten his first image, and they were super excited. This would be unimaginable to do on more of a flagship style thing where you could not ever speak for someone else's instrument. This also spoke to the fact that the kinds of observations that were planned on this team, because it required so many different people participating, ended up being largely multi-instrumental. And this was described as a form of all hands on deck or 2-for-1 science. So if they were examining a particular kind of cobble or a wind streak or some kind of stratigraphic section, they would try to use as many instruments as possible to solve that problem and get as many scientists and experts in the room as they could to help determine which observations they should get that could be used in as many ways as possible. And then unlike that instrumental metonymy where individuals were ascribed to particular parts of the spacecraft, what I noticed here was the overriding use of the word we. And we meant the robot. We also meant the team. It meant everybody. It meant the PI. It meant the scientists. It meant the scientists and the engineers. It meant the robot. It meant everyone. It was really one of those collective nouns that's very difficult to disentangle. So they would say things like, we're 4 meters away from this outcrop we want to image. We're going to do this. Then we're going to turn around. We're going to do that. And it was always ambiguous which actant it was that they were talking about. And this is going to be important later on. So let me just give you a quick sort of snapshot of what it looks like when you have moments of conflict on these teams and how it's resolved, just to give you an idea of these cultures in action. So the image on the top is a moment when on the Paris team, there was a scientist who really wanted to drive the robot up onto this little area here, a home plate. It was very difficult to get there because there's lots of rocks in the way that are going to trip up a robot as it's whirling around. So he put this image together in false color, and he wrote, this is a minimal ridge. So the whole point here is to make the rocks pop out at you so you can see where the obstacles are, and to say he's evaluated this and he thinks it's pretty minimal, maybe we can drive over it. And he showed this to the engineers, and he said, look, I'm just wondering if you guys had looked at the southern approach. Maybe this might help, right? And the engineer says, well, we've looked at all the southern approaches and we don't think they're viable. We don't want to get stuck somewhere. We can't recover. Now note the use of we here. The use of we is we the engineers, we the team, we the robot. It's unclear, right? The use of we makes an appeal to all of those things. So everybody can see themselves in this comment. And now this is actually a moment of conflict on this team. And it's a painful conflict because we have a scientist who wants to do something and an engineer who's saying, I just don't think we can do that. And this might resolve into like a cleavage between scientists and engineers, which is common in multiple missions, and which this mission does almost everything they possibly can to make sure that cleavage does not exist, so that everybody is happy at the end of the day, including the scientists and the engineers on the line. So this is a moment where like things are getting hairy and people are like holding their breaths. So as often happens on consensus-based teams, if you have a group that wants option A and a group that wants option B, and they're kind of at loggerheads, the way to build a consensus is to come up with an option C that both can agree to. And this is exactly what happens. Another scientist speaks up and is like, well, what about this alternative? This looks pretty smooth. Like maybe we could do that. And that in the end ended up being what the robot did. Okay, but let's look below. This is a moment at a meeting where members of 2 of those cross-cutting matrixed teams are interacting with each other because they're looking for opportunities to observe during each other's allocated segments. So this is a moment of like next level conflict. So we're not just looking at which scientists want to observe in their own time slot, but now groups that are like elevated up to negotiating between those time slots. And I watched them go back and forth for 2 hours as they were trying to identify places where these 2 men could find a time in this woman's timeline, basically to create these observations. And it was very sort of, back and forth. And then a third person walked by who represented another team. And he said, in mock shock, like he threw his hands up. He's like, Karen, what are you doing with these guys? They're from the atmospheres group. Like you're consorting with the enemy. And I just seen these 2 like really, go at it to try to find these moments of opportunity and get kind of thwarted and doing that. And all of a sudden it changed so that it was the group of us against you, right? And Max spoke up and said, Walter, it's 1940. This is Germany. Karen's Russia. You're England. And we've just made a pact to divide up Europe and keep you out. Okay, so note the conflict talk and the battle and the political metaphors right here in this, like, World War II reference, right? And then it's also that affective ambiguity, because they all dissolve into laughter at how stupid that is as a metaphor, and like it didn't go so well for Germany or really for Russia, so like worked better for England in the end, So there was so this is actually a humorous and lighthearted moment on the team as they're working through the difficulties of conflict and trying to make sure that conflict doesn't become relational. All right. I'll show you another moment here that was quite interesting for me, which is the notion that like these two worlds, they're operating at the same time. There's people moving back and forth between these missions. And yet they really do feel like entirely different universes at times. And the people who are on each of these missions, if they're in one mission versus the other, don't learn how to code switch between them. They end up finding the other side like utterly inexplicable. So here's a moment where I was speaking to Betty, who was a member of Helen. And Betty worked to support one of these teams, and she was really gung-ho about Helen, and she was one of those people who really was really alive with the organization, really. So I was trying to explain to her why I was interested, and that in fact it was quite different on Paris, because they would never say, they always say that they're happy at the end of the meeting. And she was like, huh, so like everyone's equally unhappy, like you've done your job well, or equally happy-ish. I was like, no, they would never say equally unhappy, because they would never say equally unhappy on Paris. It just wouldn't be possible. Oh, really? Says Betty. Like, she doesn't really believe me. I'm like, nobody ever says they're equally unhappy. They all say they're happy. That's the thing you say. Okay, so Betty tries to put this in Helen terms. Watch her do this. So the one who didn't get what they wanted, they're happy because they've been convinced the other science is more important. Like this was a prioritization thing. Like we figured out the prioritization. No, that's not really it. Okay, so my issue was fair. I had my fair chance to argue for it, and I didn't win today, but that's okay, right? So the fairness and the winning, right? Those are ways of thinking about this kind of moment in the Helen perspective, right? But that's absolutely not how they would do it on Paris at all. There's no fairness. There's no winning on Paris. It's only ever this unilateral assent, right? And so this was a moment in which that culture clash between these two sides really, really came to the fore. Now, again, I'm not here to claim that one way of working is better than the other. So those of you watching this, you may have one style that you prefer and you think the other style is like completely crazy. And this is always the case when I give this talk. And the funny thing for me is that everybody has a different preference. They all assume that the side that they like is obviously the way forward, and the other side must be crazy. And that's always varies across every audience which side they prefer. So I'm not here to tell you which way to do it, but I am here to say that there are some important implications about how you set these teams up culturally and structurally that enable really different kinds of science. And these two teams are not just kind of interesting because that's kind of how they do things, but because there's some significant implications for the science. And that's what I'm going to get into now. So the first is, because the scientific priorities and data sets come through these different organizational processes, negotiating for resources, the science ends up looking quite different. The kinds of questions you can ask and answer on these two missions looked very, very different from each other, despite the fact that they were both operating with many of the same people and institutions and in the same field of planetary science. Now, granted, Helen was a much larger, more interdisciplinary mission than Paris was, but at the same time, the forms of science actually looked quite dissimilar. So on the left, here's an image from a conference poster that I took that involves, lots of different instruments on board this mission that are looking at different things, or they're looking at one thing at the same time through lots and lots of different kinds of instrumental lenses. They're even bringing in orbital data sets in order to kind of characterize what's going on with this particular moment on Mars. Meanwhile, on the other side of the asteroid field, this image here on the right is using the same data set, and it's transforming it as visual and as spectral data, but it's the same data set, and it's the scientists who belong to that instrument team that are the leaders of this particular publication. So ultimately, what we end up seeing is that the science either stays within a kind of single instrumental lens as a primary form, or is doing this kind of 2-for-1 assemblage. And this is aligned with two very different and yet it's equally valid philosophies of science on both teams. On the Paris mission, the idea is that whatever the team has decided together is clearly what's best for the spacecraft, and it's what's best for the science. So whatever has come through our consensus process is clearly the best science that we can possibly do with this resource on Mars. Meanwhile, on the other side of the solar system, I was in a meeting once where a scientist was trying to look for consensus around an issue. And another very senior scientist spoke up and was like, look, I just don't think the process of science is well served if a bunch of people get together and say, let's agree not to disagree. You know, science is bold conjecture and refutation. We should be holding each other's feet to the fire. That's how we know we're going to get closer to the truth. And that's how we know we're going to be doing better science. So again, these are both completely legitimate philosophies of science. And if you go back into the philosophy and early sociology of science, they correspond really nicely to Mertonian and Popperian norms of how we should be doing science. So they're very, very clear. And yet they're very specifically associated with these two different teams and legitimating the kinds of science that emerges from those missions. What this also means is that the data that emerges from these two different processes is also stamped in a way that's concordant with the social relations. So what you're looking at here is functionally the equivalent images, right? If there's a visual image taken by the camera and then overlaid on top of that is thermal data from a thermal instrument. The one on the left comes from Paris. This instrument is this image is a dime a dozen. There's a special function and some software that you can get, and you just press a button and it instantly overlays the spectral data over top of the visual, so that you can get this really interesting information about the fact that, you know, things that look different in terms of their topology or in terms of their geomorphology actually have different thermal properties. Like, that's important to know, right? The image on the right actually is fairly unique, and it took several months to negotiate over email how this image would be composed, who would have ownership over the data, where the data would move, which calibration algorithm would get used. Basically the issue on the Helen team was that coordinating observations were really a major political issue, because you had to go across these autonomous units that fiercely defended their autonomy and their own local ways of determining fairness, and their own local ways of determining prioritization. At the same time, of course, on Paris, the notion was that if you limit yourself to one instrument, that's foolish. And I remember sitting with a scientist as she was like busy training herself up in an entirely other instrumental perspective and other instruments suite of tools in order to get good at doing more than one thing at a time. What this ultimately means is that the data sets that result look quite different in their characteristics. And as one scientist put it to me, he was like, who used both of these data sets, he said, well, the thing about Paris is it's very broad, but it's not very deep. Whereas Helen is a much deeper data set, but it's harder to get integration across multiple different perspectives. And this is completely the case. You can imagine that if you wanted to come in and get thermal stares of all the rocks in a region in a Paris meeting, you would be out of luck. And in fact, I observed someone attempt to do this, and people were just shocked because this person was railroading everybody else's observations and nobody was happy, and it just was a complete violation of the social norms. Instead, what that person had to do was make those observations seem central to everybody else's questions and like one key piece of the puzzle that everybody else was working around that made the instrument so central to a particular investigation. So it's really, really good at if you want this one rock and you want to see it through all the different ways possible, you got it. But the cataloging or encyclopedic nature of that emerges over time as a second order phenomenon. Similarly, on Helen, the second order there really is the ability to integrate between instruments, because for many, many different reasons. On the one hand, because the instruments are so autonomous, and the other because they're pointing in different directions. So how are you going to observe at the same time? Also, those instruments require really different phenomena from the spacecraft. I was there finally when the ultraviolet and the infrared instruments people sat down together and tried to figure out how to observe the aurora at basically the same time. And they both had to accept downgraded data and use their instruments in kind of unusual ways in order to make that happen, because it had never really been part of the plan from the beginning. The one exception here is the physics team on the Helen mission. And just like how every one of those cross-cutting teams defends their right to make these decisions in their own way, the physics team operates much more like Paris. They have they share data in a kind of downgraded database. They have many, many different people on their publications that represent many different instruments. And they have a very different style of working than many of the other, especially remote sensing instruments on Helen. And this becomes important because you can actually see these distinctions when you do a social network analysis of the co-publications. So these are two matrices that reflect the co-publications on both of these teams. This takes a view over, I think, the first 10 years or so of the mission, and it looks at a threshold of 10 co-publications together. So each of the dots you're seeing is an author node. That's an individual scientist. On the left, they're sized differently according to their centrality in the network, and actually the smaller of the three dots in the middle is the PI. who's turns out to not play the most central role in the mission. In fact, the deputy PI and the camera lead also play really central roles, largely because this is a highly densely interconnected network. It's a little over one, like hop from one person to the next. Almost everybody is interconnected. The colors is the computer trying to figure out if there's particular kinds of clusters, and the real clustering here is between basically the remote sensing and the optical instrument suite and the more physics instrument suites. But you can see that because of all the ties between them, they're thickly interconnected, these people are publishing together all the time. The data coming from those different instrument streams are working together a lot. And in fact, the deputy PI here, who's one of the larger nodes, was also working with orbital data assets at the same time. So he's a central node because he's bringing in multiple other assets as well. The image on the right, though, is the Helen team. And this actually looks almost exactly like basically every other flagship mission. We ran several flagship missions through a social network generator, and this is what we got. So the computer has exactly identified the clusters of the science instrument teams that are distinct. They are being held together in the top left by interdisciplinary scientists, who are the only individuals who are allowed to occupy more than one team position at the same time. The cluster at the bottom right are the physics instruments. Remember, I told you they worked a little bit more like Paris, and so that you can see that in their network diagram. And the key nodes in the middle actually are new bridge ties that emerged later on in the mission as the group tried to produce some form of synergistic science around Saturn's aurora. So remember, I mentioned that those two instruments wanted to observe the aurora at the same time. So those bridging nodes in between actually emerged as a result of that strategic orientation by the project to get more of these two different sides working together. I want to address two other key issues, and one is the role of the spacecraft itself. So when I first started talking about this stuff to scientists on these teams, they said, well, yeah, but that's because they're two different spacecraft, right? Like if you're a rover, you have to operate as a sort of unilateral thing, and you have all the time in the world to stop and wait while you figure out what your consensus is. But if you're whipping around in the system like at thousands of kilometers an hour, like you don't really have time to come to consensus, and it's really different. So in the book, I actually unpack that statement a lot more because I think that's the way that members of these teams naturalize their interactions as because of or as a result of their robots. But in actual fact, we've now flown rovers that operate like Helen, and we've now flown orbiters and touring vehicles that operate like Paris. And interestingly, the network diagrams, the interactions are much more consistent with the organizational form than they are with the form of spacecraft that it is. So it is not the case that all orbiters have to behave this way and that all rovers have to behave the other way. Instead, what's more likely the case, and that I unpack in a lot more detail, I'm happy to talk about in questions, is that the organizations are driving the ways in which people embody and relate to these different spacecraft. So in particular, that kind of unified, we are the robot, we're looking out over the terrain, etc., on Paris made it so that people actually brought the robot into their own bodies. And in this image, you see someone playing their hands behind her. This is an instrument operator who's trying to get a sense of where the solar panels are on this vehicle. And so people would actually, get sick when the robots weren't well, and they would break their legs when, something had happened to the robot's wheel. And they would narrate this as a kind of interplanetary connection that tied them to their robots. Meanwhile, in the Helen team, there was no such association. People would hold the spacecraft as far away from their bodies as possible using the right-hand rule to see how it moved. People also had various different helps and assistants, like a mug that showed where all the instruments were, or cardboard cutouts, etc. Because the key thing for Helenites was really trying to understand how it was going to move in this three-dimensional space, but also how the trade-offs could happen between instruments and whether or how those would be possible and fair. So the spacecraft was more of a calculator for them to try to determine how to maintain those fair relations on Earth. What this meant is that there were very different discussions about what the instruments, what the spacecraft meant to members of the team. On Paris, the spacecraft was the glue binding the team together. And once the robots leave Earth, the team is all we've got. And there was this really strong association between the health and the happiness of the team and the successes of the robots. Meanwhile, I remember someone saying quite directly, well, of course, on Helen, the emotional commitment isn't to the machine, not like those rover people. The emotional commitment is to the project. That's where we have all this affect. That's where we have all those relationships we're maintaining. The machine isn't representing that for us. And that's much more consistent with the organizational order than it is with the physicality of the robot. And finally, I want to note that these two different orientations have significant impacts on the careers of planetary scientists who move through them. Scientists have to behave in ways that are consistent with the organization. Watching people code switch and move back and forth between these two different teams was really illustrative because it meant they would actually take on these different ways of interacting, not based on who they were outside of the mission, but based on who the mission needed them to be in order to be successful. And I saw this occur in many different ways. I saw this occur with a scientist who was on Paris, who had been a former army officer and described that, now he had this role where he was, chairing these leading these mission meetings, and he needed people to feel like he was open. So he always put a smile on his face when he talked on the phone so that people could hear that he was open to their participation, right? Because he didn't want to sound gruff. So there was a kind of flattening of that affect as people moved into the Paris space that meant that people worked together in this very sort of genteel kind of way. Meanwhile, on the Helen team, individuals had to get pretty assertive in order to assert what they needed. And as one scientist who was in a senior position said, "My job is to present my team's case, but I feel like I'm not being listened to. So I get louder. And then pretty soon everyone's looking at me going, what a bitch." And so meanwhile, I want to say, "I'm sorry, but you made me this way. I have to act this way just to make you pay attention to me." You develop a reputation. Now, what's tricky here is that science is a reputation-based economy. How we behave in these mission teams becomes the reputation that moves with us throughout our careers, especially because these mission teams endure and they last for decades in many cases. And so the ways in which we are expected to behave on these teams can ultimately impact what kind of reputation we have outside those teams as we move through planetary science as a professional. What I did find was that there were strong friendship networks based on affinity, based on similar personal characteristics. For instance, you'll note everyone in these pictures is white. Many of them sort of act or dress in very similar ways, and they form part of these friendship networks that assist individuals as they move through the organizations. They assist largely in buffering those organizational challenges. This was especially the case for these three women here who are members of what they called the Old Girls Network, in which those women were able to take on very tough positions and organizational roles, but by virtue of their networks and relationships with each other, they were able to make calls that were difficult without accruing difficulty to their reputations, without accruing a form of stereotype threat. So this was actually a success story to a large extent for women in science, despite the fact that there are also these other kinds of pressures associated with affinity as people moved through these groups. I'm happy to talk more about that in questions. This is a lot to throw at you, though, so I just wanted to wrap up with some key implications for you in the teams that you're assembling and the teams that you're working in. First, if the mission organization you're in is shaping the kinds of questions you ask, the data you return, the science you do, and even the scientists that you're training as the next generation of scientists, then maybe we should start thinking strategically about how to leverage the best of these different organizational forms to achieve scientific goals. Right now, we all have a mission that we want to see fly, and suddenly there's a discovery announcement, and so we write it for discovery, and then it's New Frontiers, and so we rewrite it for New Frontiers, and then there's possibly a flagship thing, and so we rewrite it again, right? And instead of just shifting the shape of the organization every time and thinking just about the science goals, could we match science goals to an organizational form? Could we vary between the encyclopedic and synergistic views to give us a more detailed sensibility of these planets? Because Mars and Saturn now look like very different places based on what we can and can't do with the data that's returned. And remembering that these are like petri dishes for the next generation of scientists as they learn how to collaborate and they meet each other. What can we do to leverage social science insights to encourage success, particularly for women and particularly for visible minorities as they're moving through these teams? I want to give you two examples of missions I'm currently working with to show you how these insights can be put to good use. So the first is the APL's Interstellar Probe mission, and this is a mission that's trying to send something out to the interstellar medium. It's going to take at least 50 years to get there. They're all going to be dead by the time they get there. I think this is why they call it the sociologists. It's largely physicists and heliophysicists, and we know that they prefer to work in a much more Paris-style organizational structure. We actually call this particle physics exceptionalism. We see this repeatedly in particle physics experiments. But collectives are really bad at enduring over time. Bureaucracies far outlast collectives, so they're going to have to bureaucratize early as part of their key organizational form in order to make it for 50 years. So what can we bring from Helen's matrix organization, which enables that kind of bureaucratic structure at the same time as enabling visibility across those different groups to work together to enable both long-lived science and cross-cutting science? So that's one thing I'm working on with this group. At the same time, I'm working with the Europa Clipper team, where they have a strong heritage in Helen and Helen-style missions, and they are a flagship. but their level 1 science goals require a synergistic instrumental approach. They need instruments to work together. They need instruments to be giving data to each other. They cannot solve their level 1 science questions with single instruments alone. So what this means is we have to introduce a bunch of cultural elements in order to incentivize more Paris-style science to meet the level 1 requirements on board Clipper, and that needs to start at the very beginning. So hopefully this has given you a sense of some of the ways that we can think sociologically, rigorously, and organizationally about the different teams we find ourselves in. But hopefully it also helps us think a little bit more about the larger context of the teams that we're operating in and the ways in which we can tweak that organizational context, the ways in which we can contest it, the ways in which we can make changes in order to see the kinds of science that we want, the kinds of data that we need, and the kinds of scientists we'd like to foster for the next generation. So thank you, and I'm happy to take questions.